Anti-lock braking system, or ABS for short. You've most likely heard about it, and if you drive a car or modern motorbike, you've probably used it before. But how does it actually work? How do anti-lock brakes work? ABS uses wheeled speed sensors to determine if one or more wheels are trying to lock up during braking. If a wheel tries to lock up, a series of hydraulic valves limit or reduce the braking on that wheel. This prevents skidding and allows you to maintain steering control. Seems simple enough. I set about 3D printing and CNC cutting various parts of the mechanism that would be able to release the tension in cable operated brakes. The reason for choosing cable operated brakes was because I didn't want to mess with the hydraulic brakes on my newer DIY electric bike. Plus, the bike I want to test this on has narrow road tyres, in the hope they will have minimal grip on bad surfaces. But it wasn't long until I encountered my first issue. So this is the ABS mechanism which will release the tension in the brake cable, but there's one major flaw with this design, in that the stepper motor is not strong enough. I originally ran this stepper motor, which has 1.2 Newton meters of torque. This new one has 2.8 Newton meters of torque, and it still isn't enough to hold the brake tension. If I pull the rear brake, it loses steps. So I'm going to have to redesign this whole mechanism. I then redesigned the mechanism to give the stepper motor a greater mechanical advantage, using different lever lengths. This meant the motor had to rotate further, but also applied more force to counteract the tension in the cable caused by my hand, which would also mean the response time would be slightly longer. But that was the least of my worries, because I didn't realise how terrible rim brakes were after riding on wet grass. I wanted to test the system on the rear wheel, and the only way I could get it to lock up was by shifting my weight upwards and forwards temporarily to lift the rear wheel off the ground, which was pretty far from ideal. So after adjusting the mechanism about 4 different times, I decided to scrap that and move to a bike with hydraulic disc brakes. If you're one of my subscribers, you'll most likely recognise this as my homemade electric bike. But for this video, I've removed the drivetrain as the high voltage batteries were interfering with the ABS electronics. To accurately measure the speed of the wheel, I've made this 3D printed disc with 120 slots in it. Mounted to the fork is a sensor which has an infrared beam, and this infrared beam shines through the slots in the disc. When the wheel spins, and the beam is either broken or made, the sensor outputs a high or low signal. This can then be used to calculate the speed of the wheel up to 50 times per second. Interestingly enough, I noticed this exact same speed measuring technique being used on a motorbike with an anti-lock braking system. Moving up the frame, there is a black box which contains the electronics, which will control the ABS system. Inside the black box is a Tinsy 3.6 board, which will run the Arduino code. And it also has an SD card slot, so I can do data logging of the tests to hopefully optimise the system. When the Arduino code realises the brake needs to be released, it sends pulses to the stepper motor driver, which is inside this large heatsink. That then sends power up to the motor mounted on the handlebars to rotate. The mechanism to release the brake is really simple. It's just a long lever which is clamped to the brake lever that is attached to a short bit of rope. The rope will allow the brake to be used as it normally does, but when required will allow the motor to winch the brake lever, opposing the force from my hand and releasing the brake. Before I give this system a test, let's talk about how the activation of an anti-lock braking system might actually work. So you have a vehicle travelling along at a constant speed, and the rotational speed of the wheel is relative so that the outermost part of the tyre is moving backwards at the same speed as the road is, relative to the car. When the brakes are applied, if the friction between the tyre and the road is too low, the wheels will slide. But how does the ABS electronics actually detect this and know the wheel is definitely sliding? It's actually quite a complex question to answer, so let's work towards it using a few somewhat logical approaches first. An initial observation would be to say that the wheel is sliding when the speed of the wheel equals 0, when the wheel stops rotating. And because I've got a speed sensor on the front wheel of my bike, what I can do is I can program the electronics to release the brake when the speed goes to 0. Now what I'm actually going to do is program it to release the brake when the speed is below 0.5 meters per second. It's about just over 1 miles per hour. And the reason for this is sometimes the sensor might read 0.0001 meters per second and won't release the brake. So the brake will be released when the speed is below 0.5 meters per second. Let's give this a test. Okay, so those tests were pretty successful. It proves that the mechanism is able to release the brake pressure from my hand and get the wheels spinning again. The only problem is that it was very slow. The time taken from when the wheel had fully locked to when the stepper motor started to winch the brake lever back was about 0.22 seconds. And the total time that the wheel was locked for was 0.45 seconds. So the wheel was skidding for almost half a second. In terms of the mechanical response time, which is the time taken for the motor to rotate and pull the lever away from my hand, that's going to be very difficult to improve without extending my budget even further. I've already bought 2 different stepper motors for this project, and to buy the next step up in torque is going to cost way more than I want to spend on this project. So what I'm going to try and do is focus more on the electronic response time. The stepper motor takes about 1/4 of a second to react and fully release the brake. So if we can take that electronic delay time down, then hopefully we should be able to get a pretty good anti-locking brake system. So how can we detect that the wheel is going to skid before it actually happens? Well, let's take a look at the data logging. This graph shows the speed of the wheel over time, and we can see there is a large drop in speed as the wheel locks. When the speed is below 0.5 meters per second, the brake releases. It then speeds back up to match the speed of the bike, and the brake is reapplied when the speed is greater than 0.5 meters per second. So to improve the response time, we need to trigger the brake release right at this point on the graph. Let's see if plotting the deceleration of the wheel will give us a better indication. This acceleration graph shows 3 clear troughs and peaks, which display when the wheel is either slowing down to a skid or speeding up to match the speed of the bike. How about we set a deceleration limit, which will trigger the brake release? For example, if the wheel decelerates quicker than minus 10 meters per second squared, the brake will release. This time, the stepper took 0.11 seconds to start moving, which meant we've cut the electronic response time in half. But there was a small issue. It only fully released the brake once. Okay, that time it released twice, but it still didn't release on the final skid. Maybe 3rd time's the charm? Right, I've analysed the data and the slow motion footage, and what I've realised is that the deceleration is just a peak value, or well, a trough value because it's negative. But basically what this means is that the brake only releases temporarily. It doesn't hold the brake open until the wheel speed increases again. So as soon as it detects the deceleration going really low, it basically just releases the brake and puts it back on instantly. And that doesn't allow the wheel enough time to get back up to speed before reapplying the brake. This could be fixed by adding a small delay to how long the brake is disengaged for. For example, the brake could be disengaged for 1/4 of a second, so the brake gets released and then it waits for the wheel to get back up to speed and then it's reapplied again. But the problem is with this is that in some conditions the brake may just be deactivated for 1/4 of a second for no reason and could therefore extend the braking distance of the bike. So by now you're probably reconsidering how simple anti-lock braking systems actually are. And before I did the research for this video, I actually thought the same thing. Now, throughout my research, I found many different solutions of how you can detect when the wheel is about to skid before it actually does. But the majority of them all seem to boil down to one variable, called the slip ratio. The slip ratio is the ratio of the speed of the wheel versus the forward speed of the car. If the wheel isn't skidding, so it has full grip with the road beneath it, then the slip ratio will be 0. If the wheel speed is 0, so it's fully locked and it's sliding across the road, then the slip ratio is 1. Now the ideal slip ratio will depend on many different factors, and if you search slip ratio into Google, you'll most likely see a graph that looks like this. Now what this graph means is that the slip ratio can have a small range where the wheel can actually rotate slightly slower than the forward speed of the vehicle. But if it goes outside of this range, where the wheel speed is much slower than the forward speed of the vehicle, then the wheel must be coming to a stop and therefore going to start skidding. So that sounds pretty simple then. If the wheel is spinning slower than the bike is moving forwards, then I just need to release the brake pressure and I should be able to stay in control. But unfortunately, it's not that easy because I can't easily measure the forward speed of the bike if a wheel is sliding. With a car, you have 4 wheels, so if one wheel slides, you then have 3 other wheels to measure the forward speed of the car, which you can compare those 3 wheels to the wheel that's sliding and release the brake on that wheel. But with a bike, because the front wheel is the most important wheel not to slide, you only have the rear wheel as a reference. And if that rear wheel lifts off the ground or locks itself, you now have no other reference to detect or measure how fast the bike is travelling forwards. So here's my plan. Inside the box where I mounted the electronics, I also mounted an accelerometer. This will be used to measure the deceleration of the bike. Now what it's going to do is when I press the front brake, there will be a deceleration which will enable ABS activation mode. What this will do is it will save the initial speed of the wheel before it starts skidding, and it will also start a timer. Now because we can calculate speed by multiplying acceleration by time, we can then take the initial speed and subtract the acceleration times the measured time from that period. So we can basically estimate the speed of the bike going forwards from that initial ABS activation point. This is all theory, but because I've had the accelerometer mounted on the bike from the start, I've actually applied this theory to the previous data logs of the other tests, and it's looking pretty promising. So what I'm going to do is set it up to release the brake when the speed of the wheel is below this estimated speed of the bike, because then it must be skidding. So what I'm going to do is I'm going to write the code to program into the bike, and then we can give it a test. That looked pretty good to me. Let's give it another few tests to check the reliability. That works so well. Okay, so that was 3 successful tests in a row, all in control. Let's check the data and slow motion footage. From the 3 tests carried out using the slip ratio triggered brake release, the average time from the wheel stopping to the motor moving was 0.083 seconds, and the full wheel lock to release time being 0.311 seconds, meaning this accelerometer estimated slip ratio control system is about 30% faster than the zero speed triggered system. Which, considering 0.24 seconds of that time is taken for the motor to rotate, the actual response time of the electronics itself was 3 times quicker. I realise this still isn't quite enough to prevent the wheel from locking, but according to the data I've received, to release the brake before the wheel comes to a stop, the whole system would need to detect what's happening and release the brake in 0.08 of a second. Sure, this might be possible with a larger budget and more skilled electronic engineers, but for these tests, skidding for 1/3 of a second in an upright position was very feasible in terms of control. Now you might be thinking, what about different surfaces? Well, the snow isn't coming back anytime soon, so I decided to try a few different surfaces that might be experienced during everyday riding. But this made me question, do you really need an anti-lock braking system on a bicycle? In fact, I don't remember the last time I've crashed a bike purely due to braking alone. Obviously ignoring the tests in this video. Which I think is important to think about, because an anti-lock braking system on a bicycle won't guarantee grip on that front wheel. For example, if you go around a corner too quickly and have to lean over too far on a less than perfect surface, that front wheel can still lose grip and the ABS won't do anything to save you. I think ABS on a motorbike is a completely different story, because motorbikes travel far quicker and they're also more likely to have to do emergency stops. Also, the cost of an anti-lock braking system on a motorbike is far less of a percentage of the overall cost of the vehicle versus putting it onto a bicycle. Which also has to be questioned if you want to say that an anti-lock braking system is good for inexperienced cyclists. Because there probably aren't that many inexperienced cyclists that will be willing to invest the amount of money required to have an anti-lock braking system. Bosch released an anti-lock braking system for some of their electric bikes in 2018. And they even integrated an anti-over-the-handlebar system, where basically as soon as the rear wheel lifts off the ground, it will then release the brake to prevent you going over the handlebars. Now, interestingly enough, I can also implement this onto my bike because the accelerometer unit also has some gyros in it. I read a review of the Bosch e-bike system on ebikemtb.com, and they said the ABS e-bike from Bosch is the perfect solution for rental e-bikes, i.e. for tourists. And I think this is a great point, because I don't believe there are many people out there that are inexperienced cyclists that are willing to spend the amount of money you need to spend to get a bike with an ABS unit. But for tourists that may be inexperienced with cycling, I think it's perfect. So I suppose that concludes this video. It's been about 4 weeks to research, design, make this project, test it. Most of it was troubleshooting, all of the issues with the motor not having enough torque and also errors in electronic code. It drove me a bit crazy at points, but it was pretty enjoyable. If you enjoyed this video, it'd be appreciated if you could leave a thumbs up. If you're new to my channel and want to see similar videos, obviously different topics, but you know, other engineering type videos, please click subscribe down below. I need to say a massive thank you to all of my patrons for supporting me throughout this 4-week period of all of this work. I was uploading various update videos on the project as I went along, and the questions that you guys had over on Patreon really helped me steer into the right direction of what people wanted to know in terms of the topics, and also you guys gave some great suggestions in terms of getting me on the right track, because I got lost in the information at points. Yeah, so thank you very much for watching, and I'll see you in the next video. Goodbye.